Welcome to our last component to Unit 2, and that's going to be an intro to isotopes. So just to recap, the big things we've gone through so far are the subatomic particles. And you should be at a spot where you're comfortable with protons and neutrons and electrons, their charges and their masses and their locations. If you're not, now would be a good time to go back and revisit that first lecture, or at least scan through your notes real quick to get up to speed with that. The next thing that we looked at was neutral atoms. And like the name suggests, they're neutral, which is to say that they do not have a charge. Then we started to look at ions, and that was where they did have a charge. And we said the only way that you can really alter the charge is by adding or subtracting electrons. The reason that you can't change the protons, even though they've got a positive charge, is that gives the element its identity. So if we were talking about nitrogen, for example, nitrogen is nitrogen because it's got 7 protons in its nucleus, always. Can you change the charge? Yeah, but you have to do it by altering electrons. Up, more electrons, negative. Down, less electrons, positive. So the way that I always kind of tell you to think of electrons is think of them like cavities. It's counterintuitive to think, yeah, I'm adding something, but I'm getting negative. Usually we think of like more of something as positive and less of something as negative. But again, if you think of electrons as like a cavity, if I go to the dentist and he says, Cash, you've got 3 cavities. I picked up 3 cavities. Do I feel positive or negative about that? Not so good, right? I feel negative. I go get those cavities fixed. He's removed 3 cavities. Those 3 cavities are gone. Do I feel negative or positive about that? Feel positive about that. So if you're adding electrons, more negatives, you're going to have a negative charge. If you're removing them, then that would be a positive thing. Or positive charge, I should say. So now we're kind of getting back to the masses, and we're going to alter the number of neutrons. And neutrons didn't play a role with ions because neutrons are neutral. They don't have a charge, but they do have mass. You may recall that we said that we're going to say a proton's got a 1 AMU mass and a neutron's got a 1 AMU mass, and we're going to call electrons a 0 AMU, which isn't 100% accurate, but we're going to round it to 0, and look at isotopes, which isotopes are going to be atoms with an altered number of neutrons. Still can't change protons, but now we're going to see what happens if we change neutrons. So some information that you were exposed to in the lecture, but you'll want to maybe refer back to this as you go through the practice. Atomic number. On the particular periodic table I have here, the atomic number is in the top left corner, and it's arranged from small to big, small to big, small to big. Or as you move to the right or down, you're going to find an increase in atomic number, which is to say an increase in the number of protons. We've got atomic mass, which we talked about how that's the number on the bottom. And this also gives a little bit of explanation as to why we've got some remainders there, some decimals. When we know we can't have a fraction of a neutron or a fraction of a proton, why the heck wouldn't the mass then be a whole number? And the reason being is there's different versions of these that exist, different isotopes. So they took all those different types of isotopes and averaged them out. And what you wound up with is not exactly a whole number. So since there's different versions or isotopes of nitrogen, you calculate how common they are and what their masses would be and average that out, and you wound up with 14.01. So we were rounding those when we just pulled off examples from the periodic table. That would be like rounding 14.01. I'd round that down to 14. Sometimes you round up if you're at the 0.5 or higher, like boron, 10.81. Now, if I had $10.81, I'm closer to $11 than $10, so I would call that 11 AMU. So now we've got also a mass number. And the mass number is what's going to be specific to that isotope. They're saying this is the number for this version. And there's 2 ways that we can tell that something is an isotope. You might remember that we said with our ions, if you see something in subscript in the top right corner, that's telling you that it's got a charge, whether it's positive or negative, and how great that charge is. Well, there's 2 ways we can show something's an isotope. If you look at these guys, they've got numbers written off to the left. And what that is it's telling us a mass number. The other way that you could write an isotope is if someone just writes out the element that you have, dash, and then the charge. So historically, what I've seen kids mess up on is they think, oh, this is helium -3, or this is carbon -13. No, this is helium 3 or carbon 13. And if you see something written out like this with the number behind it, that's the mass number. So this is 3 AMU, or the mass is 3, not a -3. This is 13 for the atomic mass of this version or this isotope of carbon, not -13. So sometimes kids will look at these and they're like, well, there's a 15 and a 7. How do I know what the atomic number is? Well, you can use a little bit of common sense and think, okay, well, if atomic number is just the number of protons and the mass number is the protons and the neutrons, there's no way that there could be more protons than protons and neutrons together. Or if all else fails, I know that's nitrogen, and I just want to double check, I can confirm what the atomic number is on any periodic table. So looking at this particular guy, we've got 7 for our atomic number, and the mass number is given up here. So this version or this isotope of nitrogen has a mass of 15. So I put a little cheat on my periodic table to remind me when I'm calculating the number of neutrons, I take the mass and I subtract the protons. Because you may remember, we said, in the nucleus of an atom, we've got our protons and our neutrons. They're in the nucleus, or they're sometimes called nucleons, if we want to just refer to both of those in one word. And then the Bohr diagram, this is awfully simple, but it'll work for getting us through this unit of Chem A. Our electrons are orbiting on the outskirts. So if I say, hey, this is where all the mass lives, protons and neutrons both have a 1 AMU mass, electrons have a 0 AMU mass. So if this is where all the mass is, and I pull out all the protons, I'm left with the neutrons. Or if you like kind of looking at, I guess you call it a formula, you've got mass minus protons gives you neutrons. So what do we got to do here? Well, this should look kind of familiar, right? I mean, I drew up grids like this or tables for you to fill out with our other practices on neutrals and with ions. So this is how I would get moving. Atomic number, I can deduce that has to be the 7, because again, it's got to be the smaller number as your atomic number, because it doesn't make sense that I'd have more protons than I have protons and neutrons. If you're in doubt, consult your periodic table. Baboom. 7, right? Okay. So the atomic mass number, they sound pretty familiar, right? So if you need to refer back to the top here, that's okay. The atomic mass is the one on the periodic table, and the mass number is the very specific number for that isotope's mass. So atomic mass, get it off the periodic table, 14.01. This particular version or isotope has a mass number of 15. So is this an isotope? Yeah, because somebody took the time to fill in what that number is there. If I saw something up here, I would know that it's also an ion. I don't, so this is just an isotope. Number of protons, I know that's my atomic number, 7. Number of neutrons, well, if this one is 15, and I subtract out those protons, 15 minus 7, I've got 8 neutrons. And the number of electrons here, I don't see anything to suggest it has a charge or that it's an ion. That means it's neutral. So if I look at this and nitrogen is 7, there's 7 protons, it's neutral, there's going to be 7 electrons. Now, in this example down here, notice that it is also an ion and an isotope. And I know that because the charge is given to me, as is this specific mass number. So how do you go about figuring out the number of electrons? Well, remember, if this is +3, that means I got to get rid of 3 cavities to feel positive that I'm going to have to subtract out 3 electrons. And I know that if aluminum has 13 protons and there's a +3 charge on this, that to calculate the number of electrons here, it's going to be 10. what the heck's the atomic number? Well, I could look on my periodic table and see, oh, well, aluminum's 13. Or I can just kind of think it through. Makes sense that there'd be fewer protons than protons and neutrons. The atomic mass, 26.98. This specific isotope of aluminum has a mass number of 28. I know my protons is my atomic number, right? So there's 13. The way I calculate out the neutrons is if I take the mass and I subtract the protons, I'm left with the neutrons. So if I take 28 and 13 of that is protons, the remainder is going to have to be 15 neutrons. Bingo, bango, bongo, kids. It's just that doggone simple. And again, if you didn't catch this earlier, these are isotopes. Doesn't say anything about a charge there, so I know that the mass number for this guy would have to be 3. The mass number for this guy would have to be 13. Somebody took the time to write it out and say what the mass is. That's one of the two ways that you can designate something as an isotope. The other is using superscript on the left side. Not the right side, that's reserved for ions. Hope that makes sense and sheds a little bit of clarity on isotopes. If you got questions, concerns, let me know. Enjoy the day.